Jude from the University of Miami, and we're studying predictability of hurricane intensity. We're using ensembles, and the question we're trying to answer is, how far can we predict hurricane intensity? What's the predictability limit of hurricane intensity? That's a very important question because there has been not much improvement in hurricane intensity forecasting. So previous studies mainly used idealized models with prescribed TC environment, tropical cyclone environment, and we're using a realistic ensemble with that employs the SCEPS method. So the SCEPS method is adding random stochastic perturbations at each time step to the model dynamic fields. And for our study here, our main objective is to explore the upper bound of the predictability limit of long-lived, non-landfalling tropical cyclones. We have two ensembles here where we prescribe the SCEPS perturbations. One ensemble has synoptic scale perturbations, while the other ensemble has convective scale perturbations. So these perturbations are very small in amplitude, and the only difference is the scale of it, synoptic scale versus convective scale. Down here we see the differences or the variability in tropical cyclone track. The black line is the best track from the National Hurricane Center, and the blue lines are the ensemble members. So we see for the convective scale ensemble, the spread in track is very small compared to the synoptic scale ensemble. And very similar in the intensity. These are the maximum wind speed differences here, and the interesting thing here is that for both ensembles we have a pronounced uncertainty in terms of timing of rapid intensification. So in the end of the forecasting period, all the storms are similar, but they are the timing of the intensification is different. So in order to quantify the predictability a little bit more, we went back to the old Lorentz papers and we used Ed Lorentz's approach. So we decomposed all the vortices into azimuthal wave numbers, which correspond to scales in the vortex of the tropical cyclone. So this is wave number 0, 1, then we calculated the error on each scale, and we compared the error with mean energy, mean kinetic energy of that scale. And we did that for different times in the ensemble. And down here, this is probably interesting, is the red line is the error, and the blue line is the mean energy. And at the point where they both meet, where they overlap, that is the point where we lose predictability. That is the scale where we lose predictability. So we found that using these two SCEPS ensembles, we lose predictability on small scale, on the convective scale, very quickly, which is not really surprising. It's something we expected, and that's also in agreement with current thinking. The predictability of smaller scale components is on the order of 6 to 12 hours. The predictability of rain bands, that's the azimuth wave number 2 to 5, is on the order of a few days. And the most interesting finding that we got from these ensembles is that the mean vortex and the main wave number 1 vortex asymmetry is predictable for 7 days for a long-lasting, non-landfalling hurricane. So our ensemble, our model, can give us information about the strength of the mean vortex for a week or possibly even longer. We only ran the ensemble for 7 days out. And that's hopeful. That's a really positive result, that even though we don't get the smaller scales right, we still get information about size and the intensity of the mean vortex. Yeah, that's I would say the main take-home message from this work here.